So today we're going to be talking about battery management systems and impacts on energy storage. Um, so as introduced, I'm an engineer by background out of the University of Waterloo in Ontario, Canada. So this is me being an on-site engineer at one of our customer systems. I founded Nuvation 26 years ago in 1997. And I'm a huge fan of energy storage, both professionally and personally. So my day job, I do energy storage systems. And then after hours in hobby time, I build energy storage systems. We work on stuff like robot kegerators that are electric, or like giant mutant vehicles that we bring to various events. Here's our agenda for today. I'll start with a brief introduction of Nuvation. We're going to talk about energy storage system battery management. We're going to dive into some comparisons between passive and active balancing. We're going to look at some of those balancing impacts on ESS operation, and then we'll close with some innovations in battery management, and we'll leave time available for questions. So as I'm going through here, people can feel free to capture questions. You can type it into the chat. And if it's helpful, you can note the slide number if there's a slide you have a question on. All right, so introduction. So Nuvation as a company, been in business since 1997. Our roots started as an electronic product design company. And so in 26 years of operation, we've done over 1,000 projects for our customers. Obviously a lot in energy storage, electric vehicles, but also defense, aerospace, telecom, medical devices, lots of different projects. Then in 2008, we launched Nuvation Energy and with our battery management system line. And so we've been doing that now for 15 years. And we have sites installed all over the planet. We have 2 offices. I'm speaking with you right now out of our headquarters in Sunnyvale, Silicon Valley, California. And we also have a design center in Waterloo, Ontario, Canada. Here's what we do. So our core product is our battery management system. And we have a highly configurable BMS that's UL 1973 recognized. And it works with virtually any battery chemistry and any battery manufacturer. We also sell energy management solutions. So this is energy storage controllers for applications such as demand management, solar integration, power backup, lots of microgrids, stuff like that. And then we also have a suite of energy storage design services. And this is when customers hire us in order to design energy storage systems to their requirements. Here's a quick overview of our primary products. So we have the cell interface, which sits closest to the cells. And so that's measuring individual cell voltages and temperatures and doing balancing. That rolls up in a string to our stack switchgear. Stack switchgear is the level at which functional safety resides. So this is our UL 1973. Has inside of that all the algorithms for state of charge, state of health, balancing, as well as the power equipment, contactors, fuses, current shunt, and such like that. Above that, we have our multi-stack controller. So this is now our system level battery management system. So this aggregates up to 36 stacks in parallel. So it aggregates data and distributes control commands. And then above that, you can have our energy management system. So this is our end controller EMS. And as mentioned, we have a variety of applications that work on inside of that, such as demand charge management, microgrids, and so on. So this speaks a bit to some of our energy storage solutions and the kinds of energy storage systems that we can design. So we'll take it all the way up to designing containerized energy storage systems. So this involves for our customers research and selecting, which battery manufacturer we would recommend, which PCS we would recommend. We'll do rack design, container design, thermal analysis, take systems through UL 1973 certification, and all the things involved there. Here's an example of all our worldwide installations. And so, we've got a lot of sites in US and Canada, but then through our customers all over the planet, really. This is an interactive map on our website. And so these orange dots, you can actually dive in and it'll give you more detail on that site. All right, so let's get into ESS orientation on battery management. All right, so the BMS is really like the brains of the battery. So the BMS is really that thing that's closest to the batteries in the energy storage system. So it's the first line of defense to prevent things like overcharging, over discharging, detect thermal runaway, take a system offline. Um, and the differentiation is that an intelligent BMS can actually detect that problem long before other safety systems do, and trigger corrective action before it becomes a bigger problem. The PCS uses all the data coming from the BMS. The BMS is kind of the tip of the spear, getting all that information. And then we can track inside of this data logs if a battery is being misused in a way that will impact the cycle life. And we can use that in order to evaluate battery health and degradation if you can get all that data out of the system. So we often differentiate that there's like different levels of battery management systems. So most commonly when people think of a BMS, they think of the protection side of the system, that the BMS is going to detect over or under voltage, under or under temperature, over current situations, and open a contactor. This is maybe like 5–10% of what our BMS does. BMS does a whole lot more than that, managing all your external communications, multi-stack management, doing all your battery analytics, collecting all the data around that, and real-time control of the system. So I have to do a comparison to a brain. That the protection brain is like this, a little bit of like your lizard brain, your cerebellum, your brainstem, whereas the larger brain does a whole lot more. So your protection brain is that very basic BMS that simply disconnects contactors when thresholds are exceeded, but you don't have all this other stuff. So you don't have external communication. It doesn't do fault prediction. So it's pretty hard to build a modern energy storage system with a really basic BMS. An intelligent BMS is the much larger part of the brain, and this is where we add all the real-time analytics, state of charge, state of health, fault detection, fault prediction, and all the data analytics that goes with that. So managing the ESS battery. Taking an energy storage system out of service to perform battery management calibrations, can incur an actual system cost. So an energy storage system must deliver energy in some applications within milliseconds. So for example, if you're doing a resiliency application, you're providing power to like a telecom center or a hospital or something like that. They need to design an ESS with a PCS that offers full transfer without any glitches in power. And you don't really get an advance notice on that. So you have to be able to do that near instantaneously. And then there's applications like demand charge management, where if ESS is offline or doing other things, you actually lose revenue when this system is out of operation. So it's important to understand how your batteries can degrade inside of a system. So this shows a couple different curves. So in batteries, there's two types of degradation over time. You get a energy fade, meaning that over cycles, the usable capacity of the battery reduces. And then you also get a power fade, which is measured by the resistance of the cell increases over time. So let's dive into passive versus active balancing. We're going to talk about like why balancing is required at all. We're going to compare passive balancing versus active balancing, and then inside of passive balancing, there's both the traditional voltage-based as well as continuous passive balancing, and we'll get into some design considerations around that. All right, so why balance? So here's a very simple model of two different battery cells. You have your stack current, and that's going to be the same current going through both cells in the same stack. And if it was only that, then the system would stay balanced. However, cells have a parasitic battery drain of current losses modeled here in this IP1 and IP2. And it is possible for these parasitic currents to be slightly different between different cells, just due to manufacturing tolerances and chemical differences and so forth. So this is both your self-discharge, and then you also get a Coulombic efficiency, which can be different between different cells. So Coulombic efficiency is for the electrical energy that is made available to a cell. What is the efficiency as to how that is converted to chemical storage? So variations in these can result in imbalances between cells. So for example, in this application, we've got the parasitic current in cell 1 is slightly higher than the parasitic current in cell 2. That results in that cell 1 becomes empty before cell 2. The implication of that is we have to stop discharging so that we don't chemically damage cell 1. However, cell 2 still has a little bit of energy in it that we were not able to gain access to. We can look at it the other way. So in the same case, where cell 1 has a little bit more parasitic current, this is exaggerated graphically for the sake of presentation, but you can see that cell 2 becomes full before cell 1 is full, and then because it is the same stack current going through both cells, we have to stop charging at this point, because if we overcharged cell 2, it would chemically damage that cell. So if you go through a whole bunch of cycles without balancing over time, you'll end up with a very large difference in state of charge between these two cells due to the higher parasitic current in cell 1. And we've actually seen systems like this in the field where balancing was not properly tuned, and you can actually get a real impact on the usable capacity of the system. There's also current losses. So typical Coulombic efficiency numbers for lithium-ion cells are like 99.9% plus or minus 0.05%. So it's quite efficient. But that Coulombic efficiency does add up over time. So for example, this was a system that we have in the lab at Nuvation. So this is a 1500 volt LFP stack. And you can see what happened is it sat for a while, and they actually get this unbalance between your min cells and max cells. So this is actually showing the difference in those cell voltages as we go to a full charge after the system has sat for a while. And you can see you get quite a delta. This one, upper one, is going up as we get to 100% state of charge in that cell. We're actually current limiting the system as we get towards the top. So it looks like this voltage goes down. Actually, what we're seeing there is the reduction in the voltage drop across the resistance of that cell. So it looks like it goes down. So this cell would have to now be balanced to bring it down so that we can fully charge this blue cell as well. So as the battery degrades, individual cells might age at somewhat different rates. And so you get varying capacities within a stack. So let's see what happens when we discharge this two-cell module. So now we're saying cell 2 is drawn slightly smaller. It's got a slightly lower usable capacity. Its state of health is a bit lower. And so we discharge the system. Cell 2 is now fully discharged, whereas cell 1 has a little bit of remaining energy that we've been unable to gain access to that. So passive balancing is a pretty simple system. You have a switch that is a balancing switch per cell, and then you have a balancing resistor per cell. And so in this case, where cell 2 is full, we would close this balancing switch and dissipate excess energy as heat. That would make this cell have a little bit more room, and then you can apply more charging to the entire stack and bringing cell 1 to a full charge. So we can determine when to balance based on measured voltage alone or based on an imbalance prediction using voltage and current measurements. And so this speaks to the continuous balancing that I'll describe in more detail. Voltage-based balancing alone is very simple to implement, but it does require a longer period where the system is held at a high state of charge. And for some applications, holding a system in a high state of charge prevents the system from being used in its usual energy application. So in response to this, Nuvation has implemented in our Gen 5 battery management system what we call continuous passive balancing. And what this does is it does an estimation of the unbalance in a system, and then it can continue balancing without requiring the system to be held at a high state of charge. All right, so we can compare this to active balancing. So active balancing is actually charge shuttling from a strong cell to a weak cell. And so what that looks like is in this example, cell 2 is full, cell 1 has a little bit of room. And so you pull some energy out of cell 2, usually in a switched capacitor model, and then move that charge into cell 1. So the main advantage of passive balancing is the circuitry is pretty simple to implement and pretty low cost. Whereas active balancing is more efficient, that energy is not wasted as heat. But active balancing is notably more expensive because there's just more circuitry involved. Because you need a circuitry that'll move the charge from one cell to another. In a passive balancing application, the system is limited by the state of health of the lowest cell in a stack, whereas in an active balancing system, you're limited more by the average of cells within a stack. So that's one of the key advantages of active balancing. It's also important to think about current loss variations going to occur over the life of the energy storage system. So if we use passive balancing, we have a little bit of additional electricity costs to replace the energy that we're dissipating as heat. So that needs to be factored into the efficiency of the system. So this speaks to, if we show a system, this is the capacity of the cells inside of a system, and you'll get some normal distribution inside of that. In a passive balancing system, the stack capacity is limited by your cell with the lowest state of health energy, the lowest usable capacity. Whereas in active balancing, you can prop up those low cells while discharging, and so you're then limited more by the average of the usable capacity of cells in a particular stack. So an open question to consider in this is, if we use active balancing, can the balancing equipment cost be offset by the reduced cost of not having to oversize the stack? And this really depends on what the application is. What we've seen in the industry is that as node sizes continue to increase in size, the economic argument for active balancing is becoming more compelling. And so we're seeing more situations where active balancing does pencil out in their total cost of ownership of an energy storage system to really make sense. All right, so let's look at impacts of balancing on an energy storage system operation. So in traditional passive balancing, this is one of the gotchas you got to be careful about. So if you look at this system here, it looks like this green cell, cell number 7, well, it's the highest cell voltage. And so if one used just voltage-based passive cell balancing, it would look like you need to balance down cell 7. However, you need to be careful that that's actually a higher state of charge per cell rather than a higher resistance. So that same stack, as we get to the end of the charge cycle, and you've now current limited down to low charge current, I can actually see cell index 7 is buried in this group here, but it actually was not at a higher state of charge. It's actually these cells over here that should have been balanced down. And so this is one of the things to pay attention to when doing voltage-based balancing. Another thing to think about in passive balancing is this is a typical LFP cell. And as we all know, LFP cells have a pretty flat section for much of the state of the charge. And so you don't really get a good differentiation between cells. There's not a strong correlation between state of charge and individual cell voltages for LFP cells. So that makes it difficult to do balancing. You actually can really only do passive balancing in the top end here. So traditional passive balancing, it really only occurs in this top few percentage of state of charge. You can't really do traditional balancing out here because you could potentially balance the wrong cell. And then depending on your energy application, it may be impacted by that if you need to hold the system at a high state of charge to complete balancing. Some applications that's fine, other applications that's a disadvantage. So let's look at some innovations inside of battery management, because hey, Nuvation's a battery management system company. So let's talk about what we call continuous balancing. And so what we do inside the BMS is we have a model of the individual cell. And so you have the open circuit voltage of the cell, which is the actual voltage across the internal cell. The voltage that we measure is out here, but it has other components inside of it. So we have the ohmic resistance of the battery, represented by this R0. And then we also have a time-dependent voltage drop represented by this R1 and C1. And so all of these individual elements are modeled inside of the BMS such that we can calculate what the actual open circuit voltage is. So let's look at intelligent estimation. So we can be intelligent when we estimate the imbalance. And if we incorporate the OCV curve in our estimation process, we still need to get to this section. We have enough data, but we don't have to hang out there in order to do the balancing. So it's really two steps. Step one is a estimation, where the algorithm estimates the per cell imbalance, and it takes into account the cell resistance and the OCV curve. And then step two is when we execute that. And once this estimation, this snapshot has been taken, we can continue to balance over long periods of time. So we don't have to hold the system up at that high state of charge with lots of individual cell voltage data. So to compare the two, traditional balancing can only occur in this small region here, whereas continuous balancing can occur anywhere across the full state of charge of a cell. Another key advantage of continuous balancing is this is all done in software. And so this is an innovation that Nuvation has built. There's no additional hardware cost in order to implement this. This is all a software feature. So to compare what this looks like and the impact on uptime, so if you have a continuous balancing system, you only need to go to a high state of charge every couple weeks in order to capture data as to where the system is at. This is because cells age pretty slowly. Like batteries don't change a lot cycle to cycle. They do age over time, but it's a fairly small change per cycle. And so the same cells that have a lower individual state of health or usable energy, it will stay the same largely cycle to cycle. So you don't need to update your snapshot every day. Comparing that with voltage-based balancing, you have to hold the system at this higher state of charge in order to do voltage-based balancing, and you really should be balancing the system, kind of every couple days. And so this so continuous balancing gives you, up in the range of more than 99% uptime, whereas traditional voltage-based balancing, you can take as much as 10% of the system time. We can also look at cell resistance, and so in order to have that model work, Nuvation measures individual cell resistance, and this is one of the things that we report inside of our battery management system. So we give a lot of transparency inside of the system as to everything that's going on inside. So we calculate individual per cell resistance. So this is actually data from one of our systems that we have at Nuvation. And as you can see, many of the cells follow a normal distribution curve, but out here you've got a few outliers. And so this is indicative of cells that have a lower state of health. Perhaps they've aged a bit more, perhaps they're somewhere in the system where there's additional heat, and so they're aging a bit faster, or it might just have been manufacturing differences between cells. And so getting this kind of data out of a battery management system can give an early indication of cells that may require servicing or replacement. So ahead of this becoming an issue that really limits the system, this can give you a soft warning that the next time you're out servicing the site, you may consider replacing some of these cells. This same resistance data is what's used inside of our continuous balancing algorithm in the model of the cell in order to calculate the cell's open circuit voltage. And then we'll talk about some non-standard features provided by the Nuvation Energy battery management system. So one of them is we can detect poorly connected wiring across BMS modules. So if you have a bad connection, you'll get bad data and possibly bad behavior. So we call this open wire detection. And it's one of the features that we have in the Nuvation BMS. What it does is it uses the existing balancing wires and uses a proprietary software algorithm in order to compare the voltage drop of a cell when balancing versus not balancing. So there's no incremental hardware cost for this. This again is a feature that we've implemented in software, and we've had really good success in the field with customers using this algorithm. Um, and so, for example, when we first bring a system online, we've had it where we log into the system and do open wire detection across the system, and it can actually detect slightly higher resistances inside of a system. And so we've had it where we bring up a totally new container, and we tell the customer, you know, hey, actually in stack 3, cell 17, that bolt must not be correctly torqued because we're seeing a notably higher open wire result. And the customer goes over and puts a wrench on it, and they're like, yeah, sure enough, that wanted a quarter turn on that bolt. So it's actually a really useful algorithm. This also can run continuously while a system is in operation. And so in mobile applications or even in stationary applications, bolts can untorque over time. And so that's one of the innovations of Nuvation BMS is we have the ability in order to measure that kind of information. We also have a contactor life tracking. So this is important to make sure that we stay within the lifespan of contactors. Contactors do have a finite life of a number of times that they can open. And actually it bins it out into different amounts of current. And so at very low currents, contactors have thousands of cycles that they can open and close. As you get to higher currents, you can do maybe 100. As you get into a higher bucket, it's maybe 10. And then at the max current of the contactor, you can get only a couple kind of openings. And so the BMS keeps track of this. Because before it agrees to close a contactor and put a stack online, it first needs to make sure that it can functionally safe open that contactor and take the system offline if there's an issue. So this is part of UL 1973 certification is doing contactor life tracking. We also have a cooling fan activation. And so the BMS is the first device to detect when there's a rise in cell temperature inside of a system. And so we can detect that and turn on cooling fans. So this allows you to, rather than have fans on all the time, is just turn on cooling fans when they're needed. So I've certainly been in my share of energy storage systems where the system's idling and fans are running anyways. So one of the advantages of a Nuvation BMS is we actually control the cooling fans as a function of cell temperature. And so we can turn on fans just when needed. Another advantage is identification of emerging issues at the individual cell level. And so an example of that was the state of health power. And so measuring individual cell resistances. This gives us the ability in order to flag cells that are perhaps aging a bit faster. And then you can schedule a service call on that ahead of it actually impacting the usable energy of the whole system. We also have the ability to detect various cell module and power cable connectivity issues. So the BMS has a variety of watchdog timers and so forth in order to detect systems like that. And one of the key advantages of Nuvation BMS is its configurability for a wide range of different battery profiles. Nuvation's BMS can be configured for virtually any battery chemistry and battery manufacturer. For us, it's the same hardware and software. It's just loading a different software configuration file in order to work with different systems and different battery manufacturers. So this has a number of key advantages. One of the main advantages is if you're augmenting a system and you're augmenting a system, say, 10 years later, you don't have to have the same battery manufacturer and don't even necessarily have to have the same chemistry. Especially if it's a string inverter system, the Nuvation BMS can install into the existing energy storage system a different battery manufacturer, a different chemistry, and still present the same hardware and software interface to higher level controllers. So effectively, our BMS acts as like a device driver to abstract the battery and the chemistry that's underneath that. So that's one of the key advantages there. So as a recap of what we've covered today, so the BMS is the first line of defense for the battery protection. So we're there sitting closest to the cells, measuring voltage and temperature, and even like slight subtleties in these measurements can be used in data analysis in order to figure out more information about the battery system. We've had systems in the field where you see slight differences in cell voltages, and you can then calculate from that differences in usable capacity per cell, and that can feed into algorithms such as your remaining useful life of a system. And this can be highly useful in doing financial analysis and economic predictions of the system. We covered how balancing is required in order to maximize the usable energy in the energy storage system. If you don't balance a lithium system, you'll get divergence in your state of charge in cells, and that will impact your usable capacity of the whole stack. We talked about the factors that contribute to the usable energy reduction. So this is variation in current losses, that is parasitic currents, as well as variation in the per cell capacity. And then we talked about when deciding between voltage-based active and passive balancing, it's important to consider how much cell-to-cell variation exists. And we talked about how continuous balancing gives you the ability to have more time. So the traditional balancing can only be performed within a small operating region, especially with LFP cells, where you only get really good correlation between state of charge and cell voltage at the outer ends, at a high state of charge or a low state of charge. And so one of the advantages of continuous balancing is that you can balance the system more of the time without having to hold the system at a high state of charge. This can give you the advantage of higher ESS uptime, in excess of 99%, because you don't have that need to hold at a high state of charge. So in all of this, an intelligent BMS can really add a lot of value to an energy storage system operator beyond simple battery protection. And I hope I've been able to present today some of the advantages of an intelligent BMS and some of the features of a Nuvation BMS inside that.